Hello, my name is Trevor Smith. I am the Business Development Manager here at Pico Technology. And what we'll be talking about in this video is the Picoscope 6000E series PC-based oscilloscopes. These are high-performance models, 4 and 8 channels, with mixed signal options of either 8 or 16 digital channels. They have a high-speed USB 3 connection to the host computer. And an important feature that we'll be focused on here is the deep memory, so up to 4 gigasamples of capture memory. So deep memory, what's it for and why do we want it? Well, in a kind of a real-world example that, just to illustrate the point, if you think of Google Earth, it gives the appearance of being a single picture of a region of the globe. So we can look here at Europe, we can zoom in to a particular area of the continent. So we're a UK based company, so there's the zoomed in area of the British Isles, and zoom in even further and we can look at our own facility here in St Neots, Cambridgeshire, where we're based. Now that of course is a very impressive, it gives the impression of a single image that was taken of the Earth, that we were able to zoom in and in and in until we got to the level of detail that was what we wanted. But of course that's not actually the way it's done. The Google Earth system works with a system of stitched images that enable, using a post-processing system, enable users to zoom in on a level of detail that they want. Now in typical electronics, that isn't the case. We've got very often the situation where we've got a single shot event, sequence of pulses in the case that I'm showing here, and we sometimes only get one shot at that event, but we nevertheless want to zoom in and in and in to see levels of detail that are really important to verify that the device that we're testing is performing correctly. So what I've got here is a sequence of pulses and some sort of clock generator down here, and it's the block of pulses is operating over quite a long duration. So we can see here we've got a duration of, let's have a look using the rulers here. So we've got just under 100 milliseconds of events that are going on in that blue block of pulses just there. And let's just capture one of those. So I've got the software set to single mode, so we'll make one capture, and there it is, it's captured that event. And to begin with, I set the Picoscope up to a relatively short capture memory depth. So I've set it up with 100 kilosamples of capture memory, which is representative of many of the oscilloscopes that are on the market today. They're fitted with that sort of memory as standard. But what it means is at slow time basis, so we've got 20 milliseconds per division with just 100 kilosamples of capture memory to play with, it means that the sampling speed with which we captured that waveform was quite slow. It was about 500 kilosamples per second. So the interval between each sample point was 2 microseconds, which if you're looking at the block as a whole, it doesn't really matter. You can see the extremities of the block of pulses, no problem. But if you want to zoom in to look at the details of what's going on in each one of those pulses, you can see actually each one of those points on the screen now that we've zoomed in by 8,000 times, each one of those points on the display is a single sample point. We're not really seeing the detail of the pulses that we might be interested in. So what I can do instead is apply, with the Picoscope, I can apply a deeper capture memory. I can, instead of 100,000 points, I can go up to, well, 1,000,000 points, or in fact we can go straight up to 1 gigasamples, and then take another capture on this occasion with a much deeper memory. So there we are. And this time what's happened is with that deep capture memory, the gigasample, we've been able to use the full speed of the analog to digital converter. So we've sampled this time at 5 gigasamples per second sampling speed. So the interval between each sampling point now is, instead of 2 microseconds, is 200 picoseconds. So this time when we zoom in on that waveform, we get a lot more information. We start to see information about the rise time, overshoot, undershoot, if there was any, and that sort of thing. So we're able on a single shot event to capture an enormous amount of information that might be useful to us in debugging that waveform. Another capability that we have that takes advantage of this deep memory is something called deep measure. So here we are, deep measure here on the display. So I call up deep measure and I get some settings. So create the deep measure. I want to make deep measurements, in this case on channel A. I'm interested in that block of pulses that we looked at previously. I define where my cycle threshold is. So let's put that at, let's put it at 3 volts. That looks about right, somewhere in the middle of the pulses. The rise and fall time threshold, either 1090 or 1080. I could give it a name if I wish to. And I want to display the cycles in the graph. So that's okay, so I can okay that and that. And deep measure now is at work analysing every single one of those pulses that we started to look at in the previous area where we zoomed it. So with deep measure turned on, what it provides me with is a table of the results of all of the pulses that were captured in that block that we saw previously when we zoomed in. So it gives me, for every single cycle in that block, it gives me the cycle number. So in this case I can go from cycle 1 and go right the way to the bottom. I can see that there are 8,146 pulses in total, and for every single one of those pulses I can see the cycle time, the frequency, the reciprocal of the cycle time, the low pulse width, the high pulse width, the duty cycle, the rise time and fall time, the undershoot, overshoot, and so on. Now we can list them numerically in the order with which those pulses occurred, but we might be interested in seeing, well, what was the fastest cycle time out of all of those 8,000 odd pulses. So if I sort by cycle time, I can see that the fastest pulse in all of those 8,000 odd pulses occurred at pulse number 816. The cycle time was 1.58965 microseconds, and of course I can do the opposite. I can find the slowest one right at the bottom. So pulse number 8,144 was the slowest pulse, which was 768 microseconds wide. And if we go back to the fastest one, we can of course do the same trick with all of those other parameters. So if it was cycle number 816 that I was interested in, if I double click on that pulse, the deep measure function zooms in on that pulse and allows me immediately to look at the characteristics of that pulse based on the parameters that we chose from the deep measure table. Now what you can do as well, of course, is to export that data. So we can export the information from the deep measure table into a CSV file that can be then analysed statistically offline to look at the characteristics of a long duration test. So just switching back to the the presentation, we've looked at deep measure, or deep memory. We've looked at deep measure for making millions, well, up to millions of measurements on a single waveform, and analysing those characteristics. And just to finish off the video here, there's a note here of the Picoscope 6000E portfolio. I mentioned that there are 4 and 8 channel models with bandwidth ranging from 300 megahertz up to 500 megahertz, sampling speeds of 5 gigasamples per second, either 8 or flexible resolution, 8, 10 and 12-bit resolution, and this 4 gigasamples of capture memory depending on the model that you choose. All models have a 50 megahertz signal generator, and you can by adding the TA369 digital pod, you can add either 8 or 16 digital channels.